Welcome to this video. In this video, we will be studying topic 11 kinetics. This is the first topic of Edexcel International A-Level Chemistry Unit 4, the first topic of Unit 4 Chemistry. And I'll try to make a whole lot of video for all Unit 4, 5 and 6 topics in the form of playlists. I'll specifically target them for the upcoming May-June 2024 examination series and candidates. So I hope this will be of help to you. Before beginning the video, I'll let you know that in this video I'll only cover from specification 11.1 till 11.11. These two will be skipped for another video, but majority of kinetics will be covered in this video. I'll try to make it as short as possible, but we cannot compromise on concept building as well. So let's see how long this video will take. And one thing you should know is concepts from kinetic 1 of Unit 2 chemistry will be assessed in kinetic 2 of Unit 4 chemistry. Alright, chemical kinetics. If you ask me what is chemical kinetics, I'll tell you it is the study of rates of reactions. In other words, it is the study of how fast a reaction takes place. It is not the study of how far a reaction takes place. We are not interested to know whether a reaction will reach completion or not. We are not interested to know whether a reaction exists in equilibrium or not. We do not need to worry about the extent of the reaction. We are only worrying about how fast is the reaction taking place. Okay. In chemistry, we define rate of reaction specifically in A levels in a specific manner. So rate of reaction is defined in a specific manner. It is defined as the change in concentration of a substance per unit time. The substance could be a product or it could be a reactant. So the rate of reaction could be expressed in terms of products like this or expressed in terms of reactants like this. You may remember this graph from Unit 2. So as a reaction takes place, the reactants get used up, so their concentration falls, and products form, so their concentrations increases. So if we want to express a rate of reaction in terms of reactants, we need to make sure we put a negative sign in front. This indicates the concentration of reactant is decreasing with time. And another reason to put the negative sign is we know the concentration, the change in concentration of the reactant is negative. So this negative and another negative will mean the rate of reaction obtained will be positive. And before progressing with the other definitions, the first thing in A2 that is a must to maintain is that we no longer need to write those long words such as concentrations. We can denote concentration using square brackets, not circle brackets, not the other brackets, not this, but square brackets. Concentrations are denoted using square brackets. Okay. Rate equation. There are many kinds of equations. Stoichiometric equation per se. Before reading much on this rate equation, I'll show you something else which will help you understand rate equation much better when I come back to this. Let's say this is a simple equation. So beautiful. Two gaseous reactants are reacting, two gaseous products are forming. What equation is this? This is the stoichiometric equation. This is the overall equation. But these overall and stoichiometric equations are often deceiving because not all reactions take place in single step. This suggests that all these react to form all this in a single step, but this does not happen in actuality. What actually happens is this whole reaction takes place in steps. So it has a mechanism. It has a real mechanism. It takes place in step 1 and in step 2. So in step 1, this reactant is reacting, two reactants are reacting to form a product. Yes, product. Look at my pointer. Product, and an intermediate. That intermediate reacts with another reactant to reform a reactant and a reactant. So if we add this up, we will get the stoichiometric or overall equation. If we add the elementary individual steps of the reaction mechanism, we get the overall stoichiometric equation. So one thing to note is that intermediates are involved in the mechanism or in the elementary steps, but intermediates are not involved in the overall equation because these get cancelled up. If we add this, this gets cancelled up. And another thing to know, probably the most important thing to understand what a rate equation is that the fact that, okay, we have established that not all reactions take place in single steps, they take place in multiple steps. Could be 4 steps, could be 2 steps, but not all of these steps are of the same rate. Some of these steps are extremely slow, some of these steps are relatively faster. And speaking in relative terms, let's see an above example. We have given these 3 students the task of making these paper bundles. You see here, staple paper bundles. So to carry out this task, they have to follow these 3 steps. They have to, step 1, collect the papers. So let's say in a room, these papers are all scattered everywhere around. Disorder, so much disorder. They have to collect it, maybe from underneath the table, underneath their bed, from anywhere. And they have to then clean up this, tidy up this, and they have to staple up this. Logically speaking, not all of these steps are going to be taking place at the same rate. For example, if we have collected up all the papers, it will not take much time for us to tidy them up. If we have tidied up the papers, it will not take much time for us to staple them up. So no matter how much intentionally we carry out these 2 steps, how fast or slow we carry out these 2 steps, they can never be as slow as step 1, that is collecting the scattered paper. So if I ask you the task that the students are carrying out, what is this one thing that is determining the overall rate of this task? Step 1 determines the overall rate of this task because it is the slowest. Okay. So relating back here, the step of the multi-step reaction mechanism, the slowest step of the multi-step reaction mechanism is the step that determines the overall rate of reaction. The slowest step of the reaction mechanism determines the overall rate of reaction. So that is why the slowest step is called the RDS or rate determining step. Okay. Now we are perfectly educated to understand what a rate equation is. So a rate equation shows the relationship between the rate of reaction and the concentration of reactants. Reactants, not products. This is how we write a rate equation. Rate equals to rate constant K, concentration of a reactant A, because square bracket means concentration, raised to the power m. M is the partial order. We will read about this later. Excuse me, I had a water break. So the rate equation only has species up to and including the RDS of the reaction mechanism. This rate equation only will have the species, reactant species, involved up to and including the RDS. Up to and including means before the RDS and in the RDS. The reactant species that have been involved before the RDS step and in the RDS step, those reactant species are included in the rate equation. So moving on. Partial order. Partial order is the power to which the concentration of a reactant is raised to in the rate equation. Partial order also tells us about the number of particular reactant molecules involved up to and including the RDS of the reaction mechanism. Moving on. Overall order of reaction. It is the sum of the partial orders. Sum of m and could be an n, mn, m plus n. So that is the overall order. It tells about the total number of different reactant molecules involved up to and including the RDS of the reaction mechanism. RDS, the slowest step in a multi-step reaction mechanism that determines the overall rate of the reaction. We have explained that perfectly fine in the previous PDF. Rate constant. It is the proportionality constant in the rate equation. Rate constant. This one. Proportionality constant in the rate equation. The value of rate constant only depends on temperature and activation energy. Activation energy means presence of a catalyst. It depends on presence of a catalyst. According to the Arrhenius equation. We will study the Arrhenius equation below, not now. One really important distinction to make is that rate of reaction varies, depends on a number of factors. Rate of reaction could depend on the pressure of a gaseous reaction. If you increase the pressure, collision frequency will increase. So rate of reaction will also depend on volume. Rate of reaction depends on concentration of reactants. Rate of reaction depends on a lot of things. But rate constant only depends on temperature and activation energy. Only these two things, as governed by the Arrhenius equation. Now, putting all these definitions into practice, let's see what we can deduce. What does rate equals to k concentration of A to the power 1, B to the power 2 say? It says that the reaction is first order with respect to A, and the reaction is second order with respect to B, and the reaction is third order overall, because 2 plus 1 and 1 plus 2 means 3. So the reaction is third order overall. One molecule of A and two molecules of B are involved up to and including the RDS. The reason I included this sentence, and this sentence is because when we are asked in exam questions to deduce a reaction mechanism, this will come of help to us if we can remember these things. Let me see the time. 12 minutes have passed. I have done 1/3 of the task I'm going to do. Okay, I'll go first. Okay, moving on. In the previous PDF, we saw that stoichiometric equations, we already know that. It is not very difficult to know a stoichiometric equation. We can collect some elements from the market. We know what these reactant elements are. We react them and we can observe the products form. So it is not very difficult to know the reactants and products of a reaction. But it is very difficult. It is very difficult to know the reaction mechanism. We cannot know the reaction mechanism out of thin air. So to determine the reaction mechanism, or to predict the reaction mechanism, predict the steps, predict the intermediates that are involved in the mechanism, we do kinetic investigations. So kinetic investigations are done to determine the rate equation. And by comparing the rate equation and stoichiometric equation, we predict the reaction mechanism. How? This is the stoichiometric equation. This is the rate equation. Since two molecules of nitrogen monoxide are involved in the rate equation and no reactant carbon monoxide are involved in the rate equation, that is why we can say that carbon monoxide must be involved after the RDS. It is not involved before or in the RDS. It is involved rather after the RDS state. So carbon monoxide is involved in this step 2. This is not RDS because this is a first step. So the fact that we put carbon monoxide in step 2 and not in step 1 was predicted using this being compared with this. Okay. So there are two methods of doing kinetic investigations. One is the continuous method, another is the initial rate method. Give me a moment. Excuse me. back. In the continuous method, the concentration of a particular reactant is followed. Could be by titration. We are titrating the reactant mixture with a titer. That is a standard solution. So we are directly determining the um, concentration of reactant remaining in the reaction mixture. That is how we are following um, the concentration of a particular reactant is being followed over time. The other reactants not being followed, those that are not being followed are taken in large excess. So even though their concentration changes, but it doesn't change significantly because they were already in large excess. So they do not affect the rate of reaction. So only the concentration of the reactant being followed, which is decreasing obviously, only that affects the rate of reaction. So we plot the concentration time graph of the followed reactant like this, and we determine half-lives. Now, in other notes, some well-renowned A-level chemistry websites or your teachers, for example, may tell you to know the equations for the half-lives. It is quite also easy to work out the equations for half-lives, but you are not expected to know the equations for half-lives. One or two times uh, calculating half-life using equation came in exam, but those times that it did came, the formula or equation was given. So you don't need to worry about that. The concentration time graph is plotted and half-lives are determined. If the half-lives are constant, the reaction is first order with respect to that followed reactant. If the half-lives double, then the reaction is second order with respect to the followed reactant. For a zero order, that means the reactant is not involved up to and including the RDS step. It is involved after the RDS step. So that would be zero order. The reaction is zero order with respect to that kind of reactant. So the graph will be a straight line with a negative gradient. And the gradient gives the rate of reaction, because drawing a tangent here, working out its gradient here, we will get the instantaneous rate of reaction. But the gradient itself is constant here, so the rate of reaction is constant regardless of concentration of R decreasing. Regardless of concentration of R decreases, the rate of reaction or the gradient is remaining constant. So the reactant R is not affecting the rate of reaction. So the reaction is zero order with respect to R. Another method is the initial rate method. In this initial rate method, we select a desired reactant and we vary its concentration, and we measure the time taken for a fixed amount of product to form. In continuous rate method, we follow the reactant, but in initial rate method, we vary the concentration of the reactant. Same as here, the concentration of other reactants that are not uh, being desired, they are being taken in large excess, so they do not change significantly, and so they do not affect the rate of reaction. So our kinetic investigations are valid for valid purpose. Now the reason we are expressing rate of reaction as um, reason we are expressing rate of reaction as 1 by T is because uh, the rate of reaction is determined by timing, by getting the time taken for a fixed amount of product to form. So the numerator is fixed because the amount of product to form that we are measuring the time of is fixed. So using 1 as the numerator is perfectly fine. So is using 100 or 1000 perfectly fine. One advantage of using 100 by T as a measure of um, rate of reaction would be that it makes it easier for us to plot the graphs. So this is quite easy concept to grasp here. And as you would expect, after we are done with all this talk, the rate of reaction against concentration of the followed reactant or varied reactant, my mistake, is plotted to find the order of reaction with respect to that reactant. So rate concentration graphs. First order for first order, second order, and zero order. These are quite common exam questions. These are not things you should skip over. These are quite common exam questions. You memorize this. Memorize the shape of graph. Memorize these statements. For a first order reaction, the rate of reaction is directly proportional to the concentration of a reactant. For a second order reaction, the rate of reaction is directly proportional to the concentration of reactant squared. Or in other words, this is perfectly fine too. And for a zero order reaction, the rate of reaction is unaffected by changes in concentration of the reactant. So concentration of reactant is increasing, rate of reaction is remaining constant, unaffected, because that reactant is involved after the RDS. It is not involved in the up to or including the slowest step. So as it is not included or involved in the mechanism up to or in the slowest step, so it is not actually affecting the rate of reaction. So that is the theory behind this. So these are quite common exam questions as well, and these answers are basically in mark scheme format. So if you would like to purchase this notes, this is basically a 11-page note. We are almost done with today's video. This is basically a 11-page note. You do not need to know read students book, I believe, if you get your hands on these notes, because I made these notes using concepts from both the George Fraser book. You may know that it's a famous book written by Mr. George Fraser, and also the student book. So stuff from both those books are used to make these notes, as well as some exam questions. And I'm not charging very much for this um, notes too. I'll be uploading these notes on PES in a day or two, and they will only be $2. Videos on other topics I will make. Those notes I believe after this energetics and then equilibria, entropy. Those are quite easy topics in my opinion. Those will be much cheaper, maybe $1 or one and a quarter dollar. But kinetics took a lot of effort for me to make this, so I'm doing $2 for now, and I may make them $1.50 uh, first for the first 3 to 4 months. Then it will be back to the regular price. Okay, continue. This is a typical exam question. Sorry for the delay. Extremely sorry. Okay. So for the reaction, A reacts with three molecules of B, forms one molecule of AB through the AB3. The following kinetic investigation data were obtained. What kind of kinetic investigation is this? This is initial rate method. Not because of this, but the concentration of the desired reactant is being varied, not being followed, varied. So it is initial rate method of kinetic investigation. Okay. Linear method of reaction with respect to A and B. Use your answer to deduce its rate equation. Look how nice it is. You just read all this stuff, and now using all this stuff, using all this knowledge you obtained from this stuff, you're going to answer this thing. Comparing experiment 1 and 2. 1, 2. Concentration of reactant A increased by a factor of 3, while this concentration of reactant B remained constant. Rate of reaction increased by a factor of 3. So the reaction is first order with respect to reactant A. Comparing experiment 2 and 3. 2 and 3. Concentration of A increased by a factor of 3, concentration of B increased by a factor of 3, rate of reaction increased by a factor of 27. So the change in concentration, or the factor by which the concentration of A was increased, is 3, and raised to the power of 1 because its order is 1. Concentration, the factor by which concentration of B was increased is 3, and raised to the power of partial order, we do not know the partial order, just denoting it as Y, and factor by which the rate of reaction increase is 27. So if we work out the arithmetics, basic simple maths, we get that the reaction is second order with respect to reactant B. Question is not finished. They have asked us to then deduce the rate equation. So rate equation equals to rate constant, concentration of A raised to the power of 1, concentration of B raised to the power of 2. This is a follow-up exam question, also taken from mark scheme, basically mark scheme pattern. Marking points suggest why the reaction doesn't take place in a single step. Oh, this is not taking place in a single step. Exactly. One molecule of A reacting with two molecules of B, up to and including the RTS. But the third molecule of B is involved after the RTS. So this reaction is in no way taking place in one step. So the reasons are, the marking points of the two reasons are, the rate equation only has 3 reactant molecules. Yes. One plus 2 equals 3 reactant molecules, while the overall equation has 4. 1 and 3, 4. So the third molecule of B must be involved after the RDS, as only species involved up to and including the RDS are present in the rate equation. This is one marking point. Another marking point is the probability of collision of more than 2 molecules in the right orientation is very small. That is why reactions do not tend to take place in a single step. They take place in multiple steps. Moving on. Arrhenius equation. We have talked about this above. Here, rate constant. It only depends on temperature and activation energy according to the Arrhenius equation. So the Arrhenius equation tells us the relationship between rate constant, temperature, and activation energy, or in other words, catalyst. Wait a minute. Okay, so we are back. We are back. Before continuing Arrhenius equation, I forgot to almost talk about something. So far we saw two methods to determine order of reaction with respect to a particular reactant. One being using the continuous method, another being using the initial rate method. But there is both of these are kind of, you could say, manual or not so mathematical in a way, but there is a mathematical or more graphical way of also determining the order of reaction. That is this method. So we use this equation, rate equation, take the logarithm on both sides, obtain this expression, and plot it in the form y equals mx plus c. So this power, which is the partial order, comes down here. So the gradient we will obtain of this graph will give us the order of reaction with respect to that reactant. Okay, now we can move on to Arrhenius equation. So this is the Arrhenius equation. Okay, where k is the rate constant. It talks about these three variables. This is the Arrhenius equation. K equals to frequency factor e to the power minus activation energy divided by RT, where k is the rate constant, a is the frequency factor. You could call it the collision frequency factor as well. You don't need to know much about it, but just know that increasing the temperature increases this frequency factor, or A, which is quite common knowledge as well. and EA is the activation energy. One thing to note is that activation energy is always endothermic because it is the minimum energy required, so it will always be positive. And this is the molar gas constant, take care of the units, and this is the absolute temperature or temperature in Kelvin scale. So this Arrhenius equation, if we take the natural logs on both sides, we can obtain this expression, and if we rearrange it in form of y equals mx plus c, we can plot this graph, and by determining the gradient of this graph, then multiplying with minus r, we can obtain the activation energy. So that is how we obtain activation energy. This Arrhenius equation also exists in a different form, in a ratio form, ratio logarithmic form. This is more helpful in calculations when the question gives us information about rates of reactions or rate constants at two different temperatures. So this is more useful in those cases. Okay, Arrhenius equation done. Now, as I was talking, that unit 2 kinetics 1 often comes in unit 4 kinetics 2. This is the live example, living example. Synoptic AS. Just read through these. These are all mark scheme phrases, mark scheme points. Nothing difficult. You know most of these from AS. So have a go at this. But just increasing the temperature shifts this Maxwell Boltzmann distribution curve to the right and downward. So this area of the molecules with energy equal to or above the activation energy, that area increases. Now, types of catalyst. You may have read this in some capacity in unit 2, but this is mainly for unit 4 and unit 5. Basically, there are three types of catalysts, and to make it easy for you, first is homogeneous catalyst, second is heterogeneous catalyst, and third is autocatalyst. We'll read this later. So homogeneous catalyst, first basically catalyst increases the rate of reaction by providing an alternative route with a lower activation energy. Basic knowledge. Homogeneous catalysts are in the same phase as reactants, while heterogeneous catalysts are in different phase. You could get away with saying phase is the same as state even in A level, but in actuality, if you are interested what phase is, phase basically means whether substances are miscible or not with each other. So if they are miscible, then they are in the same phase. If they are immiscible, then they are in different phases. Homogeneous catalysts. They react with homogeneous catalysis and heterogeneous catalysis. You do have to know the mechanism by which homogeneous catalysts work and heterogeneous catalysts work. You have to know these mechanisms. I have written this pretty briefly, just 2 points. So because I have taken them from the mark scheme. So homogeneous catalysis. Okay, these catalysts react with one of the reactants. Okay, this is the overall equation. This is the elementary steps, or this is the reaction mechanism. Catalyst. So this catalyst reacts with one of the reactants and forms a product and an intermediate. This intermediate then reacts with another reactant and reforms the catalyst. So it may sound quite counterintuitive from what you know in AS that catalysts don't react, they are inert, they just increase the rate of reaction. However, that is not true, that is not necessarily true, because homogeneous catalysts do react, they do act as reactants in some sense, but they also reform themselves at the end of the reactions. So if you react and if you then reform, then technically you're not being used up. So you're still a catalyst. So that is how homogeneous catalysts work. And for heterogeneous catalysts, reactant molecules, gaseous molecules, adsorb onto the solid catalytic surface. Adsorb. Marking point is adsorb by formation of dative covalent bond. Then reaction takes place and activation energy is lowered, blah blah blah. Read this. So reactant molecules are converted into products, and these products are desorbed. Products are desorbed from the active site. These are all the marking points. Okay. Rate of heterogeneous catalyst controlled reactions depends on rate of adsorption and rate of desorption. If adsorption is too strong, then the reactants are adsorption basically does what is by getting adsorbed onto the catalytic surface, you weaken the bonds and you dissolve to free the catalytic surface. So if adsorption is too strong, then you do weaken the bonds, but you're not going to dissolve very fast. You may end up blocking the active site. On the other hand, if adsorption is too weak, then you're not going to weaken the bond within the reactants. So the rate of reaction is going to be very slow. So I hope this can make sense. And the main advantage of using heterogeneous catalysts in industries is that these catalysts can be separated from the reaction mixture because they are in a different phase, they are immiscible, and as they can be separated, they can be reused. Done, easy. Okay. This bit is not directly present in the specification. It is not explicitly mentioned in the specification, but for the sake of getting to know about autocatalysts, you have to know this reaction. You do not need to memorize what are the reactants or what are the products. You only need to understand how this thing works. So this reaction, reactants react to form these products. This is the concentration time graph. This concentration time graph was supposed to look like this for a reactant. Was supposed to look like this for a reactant, but it looks a bit different. Quite a bit different. This is because the reaction starts off slowly. Then as the autocatalyst is formed, the product autocatalyst is formed, reaction speeds up and slows down as the reactants are used up. So concentration of reactants become the limiting factor. There are three explanations of this. I have taken all of these from the George Sesar book. So this has come up in exams. These two are yet to come in exams in a more pronounced form. Hopefully, inshallah, May 24. Okay. Autocatalyst, the reaction is stored at room temperature, blah blah blah. As soon as manganese 2 ions are formed, producing catalytic amounts, the rate of reaction increases, gradient steepens, and this phenomenon is known as autocatalysis, in which a reaction is catalyzed by one of its products. This is happening automatically. You're not having to add a catalyst. You're forming a catalyst automatically. Okay. The reaction is strongly exothermic and temperature is not being controlled. Initially slow, but as it is exothermic, heat is evolved. So the temperature of reaction mixture increases as it is not being controlled. If it increases, rate of reaction increases. Rate of reaction again decreases at last because concentration of reactants fall as they get used up. If a reaction involves a solid reacting with a liquid, there might be a substance such as a metal oxide coating a metal surface. So the liquid has to first react with the metal oxide. That is not the original reaction. That is not the parent reaction. That is why the original reaction is slow. After it has reacted out with the metal oxide coating the surface, then it can react within the original reaction. So then the rate of reaction increases, then the curve gradient increases, and it decreases at last because again the concentration of reactants fall, so they limit the rate of reaction. Last thing for this video, there are different methods to measure the rate of reaction. 9 methods. The method you will use, these are basically MCQ questions. These no longer come in section B and C. They used to come in section B back in the day, in probably back older than 2016 papers. But let's continue. The method you are going to use out of all the 9 methods depends on the balanced equation or stoichiometric equation and the state symbols. Alright. So for example, if a reaction forms a gaseous product, then on the product side, the state symbol will be gas. So if a gas is formed, you could measure the rate of reaction by measuring the volume of the gas evolved per unit time. This is some apparatus level stuff, helpful for unit 6 and unit 4. This stuff came maybe, if I recall correctly, back in 2010. Something from this in a theory section B question. So that makes it more reasonable for you to purchase these notes. Okay. Measuring the change in mass of a reaction mixture. When a gas is evolved, gas is escaping, so the mass of the reaction mixture is decreasing. We are putting the reaction mixture, let's say a conical flask on top of a measuring balance, and as gas escapes, mass decreases, and we time it, the change in color of a reaction mixture. So color transmittance divided by time, transmission of color using a colorimeter over time, rate of reaction gives us rate of reaction. This is for iodine and sulfur clock experiments. We will read this in the next video. Then time taken for formation of a precipitate that may mask a cross, for example. That may mask a cross, for example. Time taken for formation of a precipitate. Change in pH, so pH against time graph using pH meter, electrical conductivity. Now in nucleophilic substitution reaction mechanisms of halogenalkenes, halide ions are formed as products, and hydroxide ions are as reactants. So there is some electrical conductivity change, even though only one ion is involved as a reactant, and only one ion is involved as a product. So the number of ions on both sides of the equation is same, but the size of the ions are not same. The greater the MR, the conductivity increases. So reactions of halogenalkenes forming alcohols in SN1, SN2 mechanisms, those reactions can also be investigated, kinetically investigated using electrical conductivity method, using an electrical conductimeter. Okay, measuring changes in optical activity, polarimetry, basically AS unit 2 physics stuff, measuring changes in concentration reactant product using titration. One specific example is the iodination of propanol that is directly involved in the specification that needs to be memorized. We will study this in the next video, as well as iodine and sulfur clock. 1, 2, 3. Important thing. Next video. Lastly, measuring the change in infrared absorption of a specific bond over time gives us a measure of rate of reaction. Done. Thank you. If you like this video, make sure to subscribe, share it with your friends who are sitting for the upcoming, let's say, Jan 2024, October 2023, or summer 2024. Share it with those friends, and consider subscribing. Currently, I'm busy, but I'll try to upload these videos as fast as possible on other topics. See ya.